So I'm starting the live stream now. Don't mind me, I'm just trying to test the audio. Just continue chatting. So for those of you joining us online, we're starting the stream now. We're just setting up. We'll take about 5 to 10 minutes to get actually started. In the meantime, just sit back and relax. Please sign the attendance form for those of you that are here in person. I don't know much of that history, unfortunately. Maybe ask Kevin. Oh, by the way, so we have some shirts that I just unboxed. So for those of you familiar with something MIT does sometimes, they throw frisbees to people that answer questions in the lectures. So if you answer a question, we're going to throw you a t-shirt. Probably Jane Street, yeah. Otherwise, we wouldn't have so many. Let me sort out the sizes. Oh, and we have playing cards. Maybe we shouldn't throw these, but if you answer a question during the lecture, we'll give you some cards to play with. Pardon, Oscar?
The cards are Susquehanna.
Yeah.
So the cards where so the shirts also.
I believe some is Jane Street, some is
Yeah, that has
seems
Sig on
both.
it.
Yeah, Sig. I think something was from Jane Street. Maybe it was just. Oh no, maybe something was from Optiva. I don't remember.
I actually haven't seen Optor merge being that frequent. They had Rubik's Cube though once. Pretty cool.
Well, I'm never gonna go short of playing cards now. Kevin will be here momentarily. Until then, you have math worksheets to mull about. So go do that. Yeah, so basically we want to give away as many of these shirts as possible, but answer a question, you'll get one. yeah, if you haven't yet, please scan, please scan the QR code.
That is what I used. I substituted that guy to the. I substituted that guy in, and I divided, and I basically said minus b equals to a half. And that wouldn't be possible if k and b are integers. So the other works like odd, equal, even. Question A is where I'm wondering if I should need to brute force it or not. I mean, question 3.
So to get a little of a background, hands up if you've seen proof by contradictions before. Okay, so pretty much everyone. Awesome. Hands up if you've had experience in competitive mathematics before. Oh, okay, only one person. That's a decent mixture, yeah. Because I'm not gonna lie, when Kevin showed me some of these questions, I didn't know how to do them at first. So we're both in store for some interesting things. Kevin, when he gets here, I keep talking about this mystical person, Kevin. He'll show up eventually. But, oh, speak of the devil. Okay, this is Kevin. He's brought some wet wipes for
No, I haven't.
oh, he doesn't have the wet wipes.
You know, before you turned up, I
No, wait, can you start the, go through the slides on intro to competitive,
Sure.
and then I'll go through the first couple questions.
Alright.
So try using the microphone.
Does it work?
Yeah. Okay. So Kevin will take.
Hello, testing. Hello, I'm Kevin. Nice to meet you all. Sorry I'm a bit late. Oh, yes. So yes, I'm the other director for mathematics this year with Brendan. We're gonna start with the workshop now. So arrows keys. So since this is the first competitive math workshop, we're gonna quickly go over what competitive mathematics looks like at uni. So why should we do it at UNSW? So first things first, this probably depends on what you're trying to get out of competitive mathematics, because everyone's different. But in general, there's a couple key points which I think it's good to do competitive mathematics for. So the first thing which I do it for is because I think it's very fun. Solving problems for me is genuinely enjoyable on the level of like playing video games or whatever. And that's definitely the number one reason I do it. But obviously some of you are looking for more, I don't know, quantitatively good reasons, so perhaps you'll be more interested in the cash prizes or the learning experiences, which definitely very good for uni. Well, it's not strictly like a subset of what you do at uni. There's definitely some intersection, but also there'll be stuff you do in competitive math which doesn't get taught at uni or isn't really useful to your studies, but the concepts you get from that I do find is incredibly useful to all your courses you do at UNSW and whatever further education you want to do with mathematics in the future. Solving real world problems, obviously it's math. Math was involved to solve everyone's problems, apart from the commerce people. We don't talk about them. Our workshops is always pizza, so that's our final reason. And as I don't know if you guys know Po Shen Lo, he's pretty famous for training the US IMO team and some other math things. But yes, he said maths is distilled thinking, which I think is a very tasteful quote. Anyways, so this is probably the only actual competition that UNSW hosts. It's called the SMMC, named after the Simon Marie guy. This is basically the main competition. It's the equivalent of the Putnam here at UNSW. And it happens in mid-October. We do run a training workshop for it every year. This is like a good opportunity to step your foot in. Companies definitely look at this because the organizers publish results on the website. And the mic seems to be like, it doesn't like me, that's my bad. Yes, there's a lot of individual prizes, and if you get your name on there, you might get internship offers since the sponsors are a lot of quant companies. Cool. So yeah, the structure is, if you guys are familiar with competitive mathematics, it'll be something like the competitions you've done in the past. But if you're not, do note that CM tends to be quite long, the tests, since it's hard to ask math problems in short amounts of time. So it's broken up into 2 pieces, which are 3 hours each. And each session is essentially, you get 5 problems, you have 3 hours to do them, so you can probably tell how hard they are. Oh, 4 questions? They changed it this year, okay. Each problem is worth 7 marks, regardless of how hard it is, but they tend to be in ascending difficulty. And there usually is an open problem which hasn't actually been solved by anyone in the world. So if you manage to solve it in the 3 hours, then you probably get some sort of like major acknowledgement. But even if you don't, it's a good chance to look at something that people haven't tried in the past, or people have tried, and you can try find new insights to it. Okay, so. The problems in competitive mathematics tend to be quite open-ended and proof-based. Solutions tend to be, well, I don't know if you guys have heard of the term ass pulling before, but essentially, a lot of the time, solutions look like, if you're if you haven't been told the solution and you just get told it, it looks like someone's respectfully taken it out of their behind and shown it to you. Sometimes the solutions look like they've just been made up, right? And it just somehow works. But the fun part about competitive mathematics is learning a bunch of, looking at the patterns, learning the techniques. And finally, when you see a new problem, you can maybe reduce it to a problem you've already seen, or you can see some sort of structure with the problem, and then you can come up with these amazing, unusual techniques and solve the problem, and everyone else can look at you and go like, what? How did you do that? Crazy, bro, you're so smart. I usually do not get that though, because my friends are dicks. Okay, and usually, yes, the problems are chosen to be quite short in description and aesthetically pleasing, but the insight you need to solve them, well, you need insight. You need to be like a genius or something. I don't know. Anyways, yes, there's a nice quote which I'm not going to read since my mouth. Alright, so the subject. This mic actually. Hello. Does this work? Yes. Okay. This guy can do. Maybe it's running out of battery and it's like auto turning off. Okay, so there are four main, very broad categories in competitive math. Those being algebra, combinatorics, geometry, and number theory. Usually people only refer to them by the first letter, so A, C, G, N. I don't like these 4 because, again, they're very broad and they don't really capture what a problem is at its core. As you can see, competitive mathematics can actually be broken down into a lot of a range of mathematics, which basically cover everything you could want to do in math. From analysis to game theory, all of those topics there. This is why I really like competitive mathematics. Problems can tend to include a lot of different topics and require you to know a broad amount of math. But also, not just broadness, you need to know the depth in all of these subjects to be very good at competitive math. Oftentimes, there'll be problems where you have to pull out some crazy theorem, looking at geometry to solve. But a lot of the times, you just need to have a good understanding of the concepts and build on from there. But yes, competitive math can be very broad, and yeah, there's the subject areas. Alright, so here are some tips about learning competitive math. So problem solving in itself is a very useful topic, which I'm sure you guys all want to learn since you're actually here. Oh, good job for coming. Thanks, guys. So strategies include practicing strategically. Yes, practicing strategically. This essentially just means when you approach a problem, you don't want to just try random things and see if it works unless you're very lost. You do want. Oh, you're gonna hand out the worksheets. Yes. Okay, so for that, there are problems where, as I said, you'll need to know some deep theory in the subject matter. These problems are not the best for beginners because typically, if you look at some question compilation online, right, they'll just be from a broad range of difficulties, and if you're a beginner, you have no idea how hard problems are just from looking at them. So I would recommend, number one, there are a bunch of really good textbooks, which I think we have a recommendation on the next page for. We'll cover that in a bit, but there are a bunch of textbooks which order the problems in terms of the content required and difficulty, and they'll give you like a quick rundown of what you need to do to do the problem, and they'll give you hints as well. So do questions from textbooks because they're written. The textbooks are written for people who are beginners. Okay, they're ordered and they'll always teach you the theory before you do the problem. And another thing is there are resources like there's a Discord server for Math Olympiad where they rank the problems in terms of difficulty. So often the easier problems won't require too much theory to do. It'll mostly just be the very fundamentals of the topic. Does that answer your question? No worries. Okay, selecting good notation. This is more for you than the marker. Markers in competitive math tend to go through a lot of hell because everyone does things differently. So they'll tend to understand whatever you throw at them unless it's like some Eldritch scroll. But for your own sake, it's good to have consistent good notation so that if you write down stuff in a notation and then in the future use the same notation for a problem, you can look at it and see the visual similarity between the structures you've written down, right? If you choose a different notation to do every problem with, it's going to be hard to find structure in that, okay? Modifying the problem is essentially taking a problem and rephrasing it or restructuring the constraints or whatever to make the problem look easier. We'll have an example of this today. Working backwards is, how many of you guys did 4U here? Mathematics. Okay, some people. Don't worry if you haven't. But for those who did 4U, this is essentially like working backwards from an inequality. You assume what you're trying to prove is true, and then you work backwards from there and see what conclusions you need to reach or we can reach from that assumption. So for example, you want to prove that grass is green, and then you know that horses eat green things. So if you can prove that horses eat grass, then you can prove that grass is green. Okay, that's a kind of dumb example, but essentially when you're working for a math problem, you don't actually have to go from what you know to what you're trying to prove. You can go from what you're trying to prove backwards to a point which is equivalent to it, and then go from where you started to what you're trying to prove. Man, why is this mic so low? I have to arch my back to talk. Sorry, guys. Any questions so far? Okay, so considering concrete examples, this is something you guys might know if you've done 108. How many of you are doing 1081 this term or have done 1081? Discrete math. Okay, some people. This is essentially proof by example. It's like an idea of that where you find some cases for which your question is correct. So for example, if you have a problem which... Can I write on this? I guess not. Oh, okay. So for example, if I'm trying to prove a statement about a function which takes integer inputs m and n, right? And I'm trying to prove that this function is equal to some expression in terms of m and n, right? And I have some definitions about the function, whatever. And I don't know where to start. I could first try and prove for the specific case where m and n, right? If I can try to prove this for when... How do you erase on this? Okay. There we go. Okay. We can try and prove the property is true for when n is equal to 1, okay? And maybe the proof for this, or it'll be a lot simpler because we've removed the variable, obviously, but the structure from this proof, and you'll notice I'm repeating structure a lot because competitive math, as with all, open-ended thinking, is about finding structure in the chaos, right? You can try and prove that this is true, and then maybe that will help you prove why fm2 is true. And then maybe this will let you use induction to prove everything is true. This is an example. Obviously, every example won't be like this. But yeah, that's what I mean by concrete examples. You can also try and prove that something isn't true by finding a counterexample, for example. Oh, I love saying example. All right, conjectures is essentially what we've done here. Where you choose a statement which is a reduction of what your problem is, or some other general statement which you think is useful to your problem, and you try and prove that. So, for example, again with this function question, if I have a function f m n and I want to prove that it's equal to something, right? I can conjecture that f of m n is less than or equal to m n. If this is helpful to my problem, I can conjecture this is true. And how you would come up with this conjecture is by trying examples. You can try a bunch of combinations of m and n and see that this inequality holds, right? If we can try and prove this, then we can work backwards to get to our original statement. Okay? Reduction to something familiar. This is something which I think comes to you after you've done a lot of competitive math. Typically, you need to have seen a lot of problems to do this technique. It's essentially where you see a problem and there's this point modifying the problem, right? essentially modify the problem to a problem that which you've seen before, or something very familiar to something you've seen before, and from there you know the solution, so you can solve it there. And this I would not recommend, reading solutions. You should only try this after you've done the problem. This is an issue I had when I was very young, where I see a problem which I thought was insurmountable, and I just look at the solution. And yes, it does make sense, but like, what are you learning from that, right? Unless you're memorizing the solutions to every problem, and even then, if you memorize solutions to everything you've seen, you still can't do something you can't see unless you know how to do this, right? Reducing to something familiar. So I would not read the solutions until you've tried the problem or found or made a reasonable attempt to it. Okay, if you've already done the problem and gotten the correct solution, then it's a good idea to see the solutions to get the different insights that the problem setters had, or to verify whether you're actually correct or not. So techniques here are, well, it's just a list. I don't think we're really gonna go over these in specific. We'll have further workshops on some of these. Why is contradiction not on here? It's kind of weird that we didn't put contradiction on here, since this is the contradiction workshop. Do you want to go through these? And yes, this is the resources I was talking about. So the slides will be on our website, by the way. But one of my favorite books of all time is Problem Solving Tactics, commonly called PST. This is a very famous book written by the team who trains the Australian International Mathematics Olympiads team. And it basically covers from the introductory level to the level you need to achieve a very good score on the national competition, the Australian Math Olympiad. There are some other books there, The Art of Craft of Problem Solving, Putnam and Beyond, which is a Putnam book, and Solving Mathematical Problems by The Tao. And obviously, you can use non-book resources such as YouTube, Problem Archives, Wikipedia, and this one I would recommend. The Mathematics and Olympiad Discord server, you can just Google it, and it will show up. And this essentially has a problem archive, and a lot of like-minded people who are making resources and solving problems on the daily. So if you want to interact on there, you can. If you want to be a lurker like me, you can also do that. Cool. So now we're going to move on to the actual workshop. Any questions from anyone? Okay, I'm going to go run to get some web wipes. Brandon, take it from here.
He's not kidding, by the way.
I'm actually going to get some.
Husband pen.
As you know, there will be pizza. No, we don't want your fingers getting dirty.
Yeah. Okay, so I'll take you through the basic theory. There's not really much here to talk about. And then we'll jump straight into some questions. So almost done just talking about math. We're finally going to do some math, which is why you're all here, hopefully. So I asked before, you said most of you have seen proof by contradiction before. The basic scaffold of how you proceed with a proof by contradiction is placed here. You assume the statement that you want to prove. You assume the statement that you want to prove is not true, and then you derive some sort of contradiction. So let me just check this. So that's the formal way of writing it out. So there's a number of different steps, but of course, better to see in practice. One question you may ask is why we would want to prove by contradiction in certain cases rather than other techniques that are available sometimes. Does anyone have an answer to that? Yes.
Much faster.
Yeah. Why much faster?
If you can look at the question and immediately figure out.
Sure. That's for more proof by counterexample though. So when you're saying you want to prove something doesn't always hold, you find a case where it doesn't hold. Yes, Fur?
Sometimes the questions are just nicely worded that if you do disprove it, then you can just, solve the question. Because some questions they ask you to find the value that satisfies it, which would be much harder. Whereas if they've given you a general relationship, if you can figure out when the rule is broken, it would be much easier.
I suppose so, yeah. The way I like to think about it, so you two can have your shirts
okay.
now. If they're the wrong size, come find me after. So if you answer a question, we'll give you a shirt. No matter how many times you answer it, you're going to get more and more shirts. And also cards if we run out, which is not going to happen. The way I think about it, as we have in the slide, if you want to look at proving something, sometimes you have more flexibility to work with by considering what happens when it's not true. You can work more with the logic. There's more freedom. There's more equations you can write out. There's more observations you can make, more insights. So you can, in this case, with what we have put on the slide, you can say there's these statements Q, which you can derive from P, knowing that it's true, under the false assumption that it is true, and then since Q is a logically incorrect statement, you can come to a contradiction. That's the way I understand it. Does anyone disagree with me? Okay, cool. Right, and then that's basically what we're using. So just to summarize, if we want to disprove P, we can use contraposition basically, right? So we assume we derive a contradiction by saying if being true implies another statement, if P implies another statement Q to be true, and we know that Q can never be true, so the negation of Q, then that implies P cannot be true. So that's the basics here. And a little example is this little emoji example here. So you're all going to be happy because you had pizza later, which means that if you're unhappy, that means that you don't have pizza. I think it's pretty simple. Anyone struggling to understand this one? Any questions? All right, so we'll jump into a classic one now. We'll spend only a bit of time on this because you've all been somewhat familiar with the types of proofs of contradiction in the past. So this isn't really the first one most people commonly see, but it is quite a classic one that appears in a lot of theory as well, not just in competitive mathematics, but also theory courses here at UNSW. So I'm sure you're all familiar with what a prime number is. Yes? So a prime number has no factors other than itself. 1 is not prime, we don't count 1. What we can do, and this is a famous proof, I believe, by Euclid, is prove that there are infinitely many primes. It turns out that there is also quite a lot of different proofs that can prove there's infinitely many primes. This is the more classical one that goes from contradiction. Again, we're going to use the assumption that there is finitely many primes, and we're going to derive a contradiction from that by showing that what types of statements we can prove from there are not valid. In fact, we would, in this case, we will construct a different prime showing that if there were finitely many, there's at least one more, okay? So we'll get started on just going through this. I won't make too many annotations on this one because it's relatively straightforward, but let me know if you have any problems along the way. So what we do basically is suppose that we do have finitely many primes, that is the opposite of infinite. So we can enumerate them from P1 to Pn. Kevin was talking about nice notation before, so have nice notation set up for the way that you define your variables. We're doing that here, P1 through Pn. And what we're going to say is using those primes, we want to show that there's, if we have here n primes, let's say what we can try to do is combine them some sort of way that gives us an n plus 1 prime. So what we need to look for is a number that is not divisible by any of these numbers. That is only divisible by itself and 1. And of course can't be 1 because 1's not prime. Does anyone remember the classical construction we make? Yes, Jeff?
Like P1 times P2 times all the way to Pn plus 1.
Yes. Let's see how far I can throw. Okay, that was a good throw. That was a bad catch. Yes, we take the product of all these primes and add 1 to it. So we can write this like this. We can also use the little pi notation. Doesn't matter too much. Then we have this construction. We would say that if there are only finitely many primes, this number we constructed cannot be prime, so it must be composite, meaning it has a factor of at least one of these n primes that we have. So why is it that we can't have any of these n primes be a factor of this number we constructed? Yes, Oscar.
I would think about this. You take out the modulus like any prime, let's say, like
Yep.
of Q. So like Q mod P1 or whatever, but you always end up with that one extra.
So yeah, if you look at any of the specific primes, you take the modulus. You're saying that if, say, Pi divides Q, you can take the modulus of both sides, you're left with 1 equals 0 mod Pi, I guess?
I'm saying if you have Q,
Yeah.
I don't know the proper way to say modulus, but if you have like Q mod P3 or whatever, you'll always be one more, like you always have a remainder of that one. Because all the rest will divide away nicely.
Yeah, I guess it's worth a t-shirt. Were you going to say something, Bert? So did you have your hand up before, Bert?
Yeah, I mean, I was just going to say that he meant iterating through all the primes, so what do you call it, P1
Yeah, so you can take the mod of each of them. Is that, you consider what happens when you take each individual mod or consecutive mod?
Like, the same number, you just take mod of each, like P1 to Pn,
Yep.
and as he said, you always have the remainder ones.
Yeah, that's right. Yeah, that's correct. Is everyone somewhat familiar with the mod operation? Yep. Anyone not familiar? Okay, we can do it explicitly. So explicitly, the way you would say it is, suppose, so what we would need is to suppose some, and we use the subscript pi, divides, so the notation you would use is divides, what is it, q? This just means pi divides q. And then what that would mean is that there's some, so this means exists, so there is some k, so some integer k such that k times pi equals q. Okay, so remember we had q was this product of these n numbers, one of which was pi, so we would say q times pi is equal to some number m times pi plus 1. Okay, all right, and this is where the idea of the taking the mod of pi comes in, where specifically what we have is m is equal to p1, p2, so the multiplication of all of them, so pi minus 1, but we're just skipping pi. Okay, so this is a formal way to do it without modular arithmetic, I guess. And then what we can say is that pi, if you take the m pi to the other side and factor out the pi, we have this equals 1. Okay, and then why is this equation never going to hold true if we have integers on either side? So why can it be that this equation is never true for integers? So pi, k, and m are all integers. Why can this equation never be true? Yes?
If you have the product of integers equal to 1,
Mhm.
must be like 1 and 1 or minus 1.
Both of them must be 1, yes.
But the prime cannot be 1.
Yeah, so that doesn't work. Yep. So contradiction, because that implies p1 equals 1. And 1 is not prime. Excellent. Shut. Awesome. Yeah, and the other methods, so that's the way to do it without modular arithmetic, which is equivalent to saying that the way with modular arithmetic, for those of you that are familiar, we'll try to like switch between those of you that aren't too familiar and those that are, is to say that for q, you would have q mod pi for any pi, any of these, I should say probably I is between this 1 and n. We would have this equal to 0 plus 1, which means that, yeah, you have a non-zero remainder, which means that pi does not divide. That's what the symbol means, q. Okay? Cool. In either case, we show that none of the pi's, none of these prime numbers from 1 to n can divide q, so we have that q cannot be composite. Right? Any objections? Okay. Awesome sauce. All right, so for these first few problems, we'll go through it with beginners in mind, but as we move on, we'll move on to some more complicated ones as we do so, and we use more complicated techniques. But for the meantime, we'll try to keep it relatively attainable. All right, so have a read of this next one. Maybe I'll give you a couple, let's say 30 seconds to think about it. So we have, again, similar kind of to before, n numbers, not necessarily primes this time, but just n numbers, which is what we could call a permutation of 1 to n, so a rearrangement of 1 to n. What that means is that if you look at the numbers from 1 to n, you would find each of those numbers in one of the a numbers. Okay? So an example, I guess on this here, is if we look at n equals 3, and you could have, say, a1 equals 2, a2 equals 3, and a3 equals 1 is an example of a rearrangement, a little permutation. what we want to do is show that if n is odd, so kind of similar to what this example we had here. By the way, for those of you joining online, we are just making some annotations on an iPad on a different projector, so that's why you can't understand some of the things that we're saying, but you, of course, can see on the slides. What we want to show is that this product is even. Okay? So let that settle in for a second. What maybe can we try? So the first thing you would probably want to think about is, if it's not even, what does that mean about every number in this product? It's maybe one of the first observations we would have to make. So we're starting that train of thought, right? We're trying to motivate by contradiction, what happens if it's not true? If it's not true, if we multiply these n numbers, so these n numbers being a1 minus 1, a2 minus 2, what can we say about all n of those? Yes. Yes, they all have to be odd. Okay, this might be hard to throw.
Are you going to take the cards or?
Oh, sure. I don't want to throw those, but you go. Yeah, if you want cards instead of the shirts, please let me know. Okay, yes, so they all have to be odd. That's our first key observation. If this is not true, they all have to be odd. So I guess making that observation is much easier than trying to look at the direct proof, which would be something about evens and odds directly. But we can make the direct observation that none of these numbers can be odd that we're multiplying. So the numbers, we have to observe if our statement's false, then ai minus I is odd for all. That's what the symbol means, I in 1 to n. Okay? So what does that mean? How can we use this information? Yes?
I just thought of a method. I'm wondering if it would make sense, but my idea was strategically, like, let's just assume in that scenario, the way all factors are odd is we don't have even factors subtract each other. We instead have like a1, a3 be even, and in that scenario a2 to a4 be odd. But there's one issue, even minus odd is still odd, because odd plus odd is even, which means that even though we made sure that the even factors will be odd, as in the a2 minus whatevers, the a1 minus whatever will have to end up being even, which will make the whole thing even.
Do you want your playing cards?
Oh, okay, but that's not a valid strategy.
Based off most of what you just said, looking at odd plus odd equals even and that type of argument, that's pretty much what we're going to do. Yes.
Oh, okay.
Yes. So we're going to make a counting type of argument. So the next key observation we have to make is if we look at the odd indices, so say, for instance, a1 minus 1, in order for that to be odd, what we have to have is a1 is even, right? So we can make the observation, so a1, a3 minus 3, odd. We could say dot, dot, dot. That means that a1 has to be even, right? a3 has to be even, and downwards, right? Any objections yet? And we can make a similar argument with the even indices. So since we have a2 minus 2 is odd, a4 minus 4 is odd, and we can continue this on. That means, for instance, a2 is odd, a4 is odd, and all the same for the even indices, okay? So we're almost there, but there's a little piece of information in the question that we haven't used yet. What is that? So we have something working, something going for us. How can we use this type of argument? So we know that of our a's, we have to have 1, 3, 5, dot, 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 to the last odd number before or equal to n have to be odd, and the opposite for the, even, and the opposite for the even ones. So what's the last piece of information in the question that we haven't used yet? Sorry for that. So what does the question explicitly tell us that we haven't mentioned yet? Yes?
Is it the fact that n is odd?
Yes. Do you want a t-shirt?
Yeah, sure.
Can someone throw it back to him? Yes, so n is odd, right? So that means that this first sequence, we go up to n plus 1. the second sequence will only go up to n. Okay, so that means that, I'll get this here, that means we have exactly n over 2, if my arithmetic's correct, odd, rounding down, yeah, n over 2, so you could say n minus 1 over 2, odd numbers, and then n plus 1 over 2 even numbers. Okay, unless I've messed something up. Yep, that sounds right. And then why is this a contradiction? Okay, wait. Yep. Why is this a contradiction? Yes.
Well, from the question, it says you have n plus 1, 2 odd numbers and n minus 1, 2 even numbers.
Yes, if you have a rearrangement of the numbers 1 to n, you would have to have the opposite occurring where you have n, wait. Oh yeah, you'd have to have n plus 1 odd numbers and n minus 1 even numbers, which is the opposite to what we have. Yes.
Multiplying any odd number by an even number
Mhm.
results in an even number.
Yes. And sorry, what's the point from that? We have more.
No, these are only two shows.
So what's your argument from there? I'm not quite following. Forgive me, I might have missed
So I
something.
meant that since we know that n is odd,
Mm-hmm.
we know n minus 1 is even.
Yes.
And we know we have an even amount of odd numbers.
Mm.
So we multiply the even amount of odd numbers together, and then we get an even result.
Well, all we have to do to show that this product is even is to show at least one of these n numbers in the product is even, right? So we've assumed that none of them are even. We've made this counting argument of what, how many of the AIs have to be even, how many have to be odd. The logic follows that n plus 1 over 2 of them have to be even, and n minus 1 over 2 of them have to be odd. But since we're dealing with a rearrangement of 1 to n, that can't be true, because in the numbers 1 to n, if n is odd, strictly more of them have to be odd than even.
I think you should just write down like the first 7 numbers to show that it's 4 and 3. Well, is that obvious?
We could do an example when, yeah, say n equals 5, then we would have to have A1, A3, A5 be even, A2, A4 odd, right? But the numbers, let's see, next to 5, that's 1, 2, 3, 4, 5, right? So there's two odd numbers here, 3 even numbers, but that's the opposite of what's happening here. So the way that we've counted how many even and odd numbers we have is in direct contradiction of what we want. Okay. Does anyone have any problems with that? Cool. All right. Yep.
Yes?
I'm not sure if this works, but could you do something like, since all of those are odd, you take the sum of them, and the sum should be 0 because the a's are a rearrangement of 1 to n.
Mm-hmm.
So the sum is even, but
Mm-hmm.
you have a
Odd number of odd
yeah,
numbers.
yeah,
Yeah.
and that should be odd.
That would work as well.
Mm.
Yes?
So can you explain again like how you got n plus 1 or 2 even numbers and n minus 1 or 2 odd numbers?
Oh, sure. So we have 1, 3, 5, 7, 9, all the way to n, right?
Mm.
Okay, again.
So the numbers A1, A3, A5, A7, so on to AN,
Yep.
whatever n is, they're all even, right? So if we do some small cases, 1, 3, 5, 7, 9, right? So n is equal to 9, and there's 5 numbers here, okay? So if n plus 1 on 2 is equal to 5, right? And you can generalize this to any number of n, right? Yeah, so it's just, it's easier to come up with these if you can't think of them straight away by writing out a few cases of n. And that's the only thing I found in the box, my bad. And yeah, same thing with the n minus 1 and 2 odd numbers. This one you can just figure it out because there are n numbers total, and the number of even numbers plus the number of odd numbers has to equal n, right? And indeed, n plus 1 and 2 plus n minus 1 and 2 is n. Is that Justin? Any other questions for this one? Okay, we're gonna continue on to the next example now. All right, a cake design is decorate. What? A cake design is decorating the top of a cake with 9 connected flat patches that can be thought of as planar surfaces. So this question, it's essentially, we have a cake, and we have 9 connected flat patches, which you can think of as, I don't know, like these little regions on top of this cake. Obviously, I can't draw all of them since I only have 5 colors. You get the idea. Right. And the union of the patches, each of area equal to 1, has a total area equal to 5. Prove that the overlap of some of these 2 patches is an area greater than or equal to 1 over 9. Okay, so this question is essentially about, where we have 9 patches of equal area on top of a cake. And we say that the total area they cover is equal to 5, right? And the contradiction here would be if none of the overlaps has area greater than or equal to 1 over 9. So let's say that's the case, okay? So suppose that the overlap of every 2 surfaces is less than 1/9, which would mean that if we have, let's say the areas, if the overlap of every surface is less than 1/9, the first area, let's say, is 1. Right? The second area can only overlap with at most 1/9 with the first area. Okay? So the second area has to have an overlap, 8 over 9, not covering the first area. Does that make sense to everyone? Okay, cool. So we'll number the surfaces, right? This is S1, S2, S1, S9. And the union has surface area greater than this because the first one has 1, second one is 8 over 9, so we add them up. Right? The union, S1, union, S2. So essentially, if we have S1 being this patch, and S2 being this patch, we're saying that the total area they cover, which is the area of pink, is bigger than or equal to 1 plus 8 or 9, 17. Okay, and you can do this continuously because if we look at S1 union S2 union S3, right? That is literally a unique patch. Now, if we look at the third region, let's say we draw a third region on here, which in, I don't know, purple. And this region has area 1, and also it can only overlap with the first 2 surfaces, 1/9 each, right? So the maximum overlap has to be 2/9, okay? So this thing here, right, S3, maximum this can be 7/9, okay? So therefore, the S1 union S2 union S3 has a total area maximum of 1 plus 8 over 9 or 7 over 9. Right? And we can continue this onwards arbitrarily until we get the sum of every single area. Right? The union of these areas is going to be the total area which they cover. But if we compute that, the sum is going to be bigger than 5. Okay? So this is a contradiction. Any questions about this one? I think this is probably an easier one to understand than the last one since it's a lot more visualizable. Whenever you get a question where you're looking at, let's say, an inequality, right? Usually the contradiction is to assume the opposite of that inequality and try and squeeze your way to a contradiction. For example, in this case, 5 bigger than 5. Okay. So, the next question. Let p of x be a polynomial of even degree and positive leading coefficient. Show that if p of x is bigger than the second diff of p of x, then p of x is non-negative for all real x.
So for this one, we'll make certain obviously understand in high school. But think about trying to visualize this polynomial look like. Given we have this restriction on it, it's going to second derivative of itself. How can we lead to a contradiction if we suppose that p of x can be negative? Okay. But it's going to come out with a So does anyone have any ideas? Any visualizations? Any insights that help? So let's try to draw it. So of course our first step would be suppose that p of x can be linear, right? So polynomials are functions in a very loose sense in terms of you can draw it without lifting the pen. So our polynomial has even degree. So what does that mean when I have to draw it? So even degree and has positive leading coefficient. What kind of sketchy shape would I have to draw? Yeah, something. Let's say like. Oh, what's this? So something like this. This is like a basic parabola. Could be degree 2, degree 6, or so forth. Yeah, it could curve down. So that's example. And what we're supposing is that if it crosses the x-axis like this, there's this point down here. There could be points, these different points that are below the x-axis. That could be it. As Kevin also suggested, we could also have something more topological that goes out like this. Okay? That's another example. But the key point in the model from high school is that if we have positive coefficient, then as x approaches infinity or minus infinity, because we would have the leading coefficient be a power of 2, would approach infinity. Okay, that's our first observation. Anyone have any other observations? Any other observations? So again, we're going to suppose that there exists a point, let's say any point down here that is below the y-axis. What can we try to do? Should we just choose any point? So example, in say this function, should we just choose any point that is below the x-axis and try to deal with that, or should we try to choose it further? So this is a common proof technique where we're trying to prove constructively or inductively, where if you're trying to look at something that exists, you want to pick a clever thing. Maybe a maximum, maybe a minimum, maybe the greatest of concept, or, you know, perfect, and that's the same thing. Yeah, the slope is 0. So a local mean, you say? My bad. That's why I really didn't want to throw it. So could we choose here, we could choose here or here, for instance. Those are like nice places to look at, right? Yeah, so, and we might as well maybe just choose the lowest one of all of them. I don't remember the next one. Oh, that's true. We could just say what. Yeah, of course. Different ways of going about it, but let's show you the actual solution first. So we look at this minimum value. Okay, let's suppose that this happened at A. Okay, so we know that since it's a minimum, okay, that means that if we talk about either concavity, it's a stationary point, or it is a stationary point, of course. First derivative would be 0, but we don't really care about the first derivative. In terms of the second derivative concavity, if you think about, say, for instance, x to the power of 4, the second derivative may still be 0 at the local minimum, but it definitely cannot be negative. It has to be positive. So it has to be either concave up, up arrows. Yeah, the smiley face. You go up, right? You go up. Or it could just be straight. So what we have to say is that at this A, f of A, so the second derivative of A is greater than or equal to 0. That's our observation. Now we have this relationship here between our.
Doesn't really matter.
This guy. Yes, p double dash of A is greater than or equal to 0, and we also know from what's given that p of A is greater than or equal to p double dash of A. Okay, and I guess we can make this chaining argument that p of A then greater than or equal to 0, which is a contradiction. Okay? Why is it a contradiction?
What did we assume about the other?
Yeah.
Well,
and particularly we assumed it was the minimum, or a minimum. if we show that for any local minimum or any minimum at all of the function that has to be non-negative, then that means that the function itself, because it's continuous in this way, continuity, that means that the function itself can never drop below the y. Any objections to that?
Yeah. So yeah, essentially the argument is, right, we assume that for some point x, p of x is negative, which means that we've crossed the x-axis, and so because we have a global minimum, due to our shape of the parabola, as we talked about up here, right, we have a local, global minimum at this point here, and we will always have. I'm wrong about the stylus. Sorry.
Sure. My bad.
No, we will have to have a global minimum, and if our parabola is ever negative, not parabola, this is a parabola, but if our polynomial is ever negative, that means that p of x will be negative at this global minimum, right? But because this is a global minimum, it's also a minimum, which means that our second derivative is bigger than 0, and that means that p of x is going to be bigger than 0, which is a contradiction. Okay. Any questions? So this is a bit more theoretical. We themed it mathematically. You can read it if you'd like. I'll give you a drawing of this, but we will have a drawing in the solution. So I'm just going to look about this roughly. Let's think about the. Do you need a?
Sorry?
Okay, there we go.
Yeah, for the line. Yeah.
Yes.
Hold it. Just hold it.
Okay, so Miles has some length of spaghetti. Let's say this is the length of spaghetti. Okay, it's a very straight span of spaghetti. Oh, what the hell?
Excuse me?
Sorry.
Bro, what are you doing?
I just pressed the keyboard and stopped presenting.
This guy, not having a good day.
Okay, sorry. And his friend Thomas suggests that the spaghetti be cut so that for every length x, let's say we have a point x here. This is the length x from the beginning, okay? If if any length x is measured from the start of the spaghetti, Paul should receive x plus a, right? So let's say Thomas gets this much, and Paul should get this much. Okay, so we'll take x, we'll add a to it, where a is some real number, arbitrary real number, and Paul should get this point. Okay, and so they repeat this process until every single point on the spaghetti is taken by one person wrong. And we're trying to show that no matter how you split the spaghetti by choosing A or by choosing the points, this is impossible, okay? And I suppose the spaghetti thing is fun, but not very mathematical, so we'll reword this. Suppose that show that for there does not exist any real numbers such that there cannot be sets B equals to A plus A for some real number A. So going by our spaghetti example, our set A would be the spaghetti that Paul receives, and our set B would be the set Paul receives. A is the set that Thomas receives. And if we draw the unit interval, we draw the interval. Set A would be some of these points here. Uncountably many of these, but they exist. And set B would be set A shifted along by A. So you can imagine that as like these points here. But every single point we have, we shifted up by A. Okay, you might not be familiar with this adding a set to another set notation, but this is essentially just B is the set of x plus A when x is in A. So we've just added A to every element in A. Okay, any questions with the premise of the problem? Okay, so I guess we can. I don't know how to bend them. Oh, there's a button.
There is a button to undo.
There is a button.
Technology, huh?
Right. So obviously this is a contradiction workshop. We're going to assume the contradiction. Suppose we can partition the interval like this. All right. Now we're going to study some specific intervals. Obviously we're going. This is not obvious. But because A and B are arbitrary sets, right? If we look at our position earlier, if blue is A and pink is B, right? If A is negative, we can just go reverse. Right? So this would be negative A downwards. So since any partition would work if A and B did exist and A was negative, we could also if A was positive. Does that make sense? We could just swap their roles essentially. Okay. Oh, sorry, I should show you guys that. So, does anyone have any ideas as to how we can construct a counterexample in this case to show a contradiction? I'll give you guys maybe 20 seconds for that. If anyone has any insights, let me know.
There's also a diagram on the slides, I think, on the next one. If you want to, yeah, try not to leak it. Some spoilers there.
Oh, disjoint means that the intersection is 0.
Triple
So,
the empty set.
yeah, it means that there is no point which is both in A and B.
Shouldn't you also take an
You said the same thing in the same speed twice. Okay, I'll give you a metronome. Okay. No. We have a magical dicer which can cut your spaghetti infinitely. Look, like the food theme was not developed until very recently. Okay, the spaghetti no longer exists, guys. I ate it. I ate the spaghetti. Okay, it's. All right, time's up. Anyone have any ideas on how we can start with this? Okay. So clearly, because we've split the set into 2 sets, right, and the set is not empty, the interval at 0, 1 obviously contains real numbers. There has to be some minimum in one of our sets. Okay, in fact, there has to be at least one real number in one of our sets. So because, I should say that. Because there is some number in our set A and B is A plus. Alright, it's okay. So B is equal to A plus A. If there did exist some, notice how from our definition of B, right? We have B is equal to X plus A. Now A is bigger than 0. In fact, A can't be 0, but that doesn't really matter right now. Oh, wait, actually it does. Sorry. And X is bigger than or equal to 0. Okay, so if B has any elements, they have to all be bigger than X plus A, which is if B is in B bigger than or equal to A. So yes. If we add them up, okay. So this tells us that the interval 0 to A, so the first bit here. Bit here has to be in the set A, okay? Because there is, if any of this was in B, then we would need to have like A be back here. Let's say we have a point here in B somehow. Then we have to go back A, and this point here would be in A. But that's impossible because this is outside of the interval. Right. So this bit is in A. What does this tell us about? Can anyone tell me if we now know an interval that's in B? So this is the formal argument. Does anyone know if we have this first bit in set A, what part of this interval would have to be in set B? Well, yes, but that's going a bit fast, Justin. Okay, what about this bit here? It's okay, it's okay. We still love you, Justin. What about this bit here? Let's say this is from 0 to A, and now this is 2A. What would this interval have to be in, by our definition? Anyone? Okay, well the first interval is all in the set A, right? Yeah, it has to be in B, because B, by definition, is everything in A shifted right by lowercase a. So this bit here is all in B, and this will be a filled-in circle at A, and this will be a circle here. And so, can anyone tell me how I can repeat this pattern until the end of the unit interval? No? That's okay. So the next A units have to all be in A because the next A units have to all be in A because if this bit was in B, right? Suppose for contradiction, this bit was in B. Then remember, well, initially, if our argument for saying that the first interval had to be in A was because if it was in B, then if we shifted left by A, it would be outside of the interval, right? So if this section was in B...
Can I just interrupt for a second?
Yes.
Sorry, Kevin. We would have checked the form, but maybe just easier to ask. Does anyone have any dietary requirements? Any preferences of pizza?
I just can't eat pork and beef. That's
Okay, we'll get one just normal. Yeah. We'll get one just...
Okay, so again, assume that there was some point here B in B. If we shift it back A, right, it's gonna land in this interval from A to B. But this bit here is all in B, right? So that's impossible. So therefore, this interval here would have to all be in B. All in A. So yes, full circle, empty circle, and so on. Okay. So our argument is this. Right. The formalization is the even intervals, so from 0 to A, from 2A to 3A, from 4A to 5A, and so on, will all be in the set A. And A to 3A, sorry, A to 2A, 3A to 4A, so on, will all be in B. Does that make sense? Yeah, we have a diagram here, which is quite better. This is what it will look like, okay? Does this make sense to everyone? Okay, cool. So now, notice we've filled in every single number except for the number at the end, 1, right? We're gonna look at the number 1. And 1 is very special because we know it has to be in one of the sets. Hold on. we know it has to be in some we know it has to be in some interval, right? Either A or B. And because it's in one of these intervals, it's in remember from our diagram back here, right? Our sets are the partitions 2k plus 1, 2k plus 2, okay? And 2k plus 1. This basically means every single endpoint of a set is at 0A, 2A, 3A, so on, to, I don't know, we'll just k minus 1, A, right? So this means there has to be some integer for which 1 is in this interval here, okay? Now, because 1 can't be at the endpoint, so what we're saying here is 1 is in some set, n a, n plus 1, a. Now, obviously 1 can't be equal to n plus 1. Okay, because that point is not in this set. Does that make sense? However, that means that the interval contains some number, a number, which is bigger than 1, okay? Because this is an open set over here, right, this is a circle bracket, there's always going to be, in some way to find a number larger than 1 in this interval, which means that we've somehow managed to color the whole interval plus a bit. Okay, that's a contradiction. Sorry, that was a bit fast. Does anyone have any questions regarding to the explanation? Does this make sense to everyone? Okay. Cool. Brendan, you want to do this so I can do this? Okay, sure. Okay. So here's a question. Prove that.
Oh, yeah, just go through the question and I'll do
Okay.
it.
Prove that the sum of these 3 irrational numbers is an irrational number. Now, please don't make the mistake of saying irrational is irrational. Irrational plus irrational is irrational. A lot of people do this, where like, I don't know, A plus B, where A and B are irrational. They look at this and go, well, if I have a rational number plus a rational number, it's irrational because the rationals are closed, right? But the irrationals do not satisfy this property. Okay. Yeah, the counterexample for that is, for example, like pi minus
67 plus pi and 67 minus
yeah.
pi.
Pi minus.
And
Yeah, let's write that down.
makes sense, Yeah.
No, wait, hold
Yeah,
on.
yeah,
hold
you
on, hold
get
on,
it,
hold
you
on.
get it now.
37.5 plus pi. Plus, no.
He's cooking, he's cooking.
Minus pi, right?
You see, you're gonna see the vision in a second.
There's
Yeah,
the vision,
yeah,
there's the
yeah,
vision,
yeah.
okay?
I don't know what's the obsession with
That's why he's my favorite director.
That's cool.
Oh, sorry, Oscar.
Well, I'm also his least favorite director because there's only 2 of them, so you know.
No, what about all the directors?
Oh, you meant like, okay. Anyways.
What do I have so?
What?
Self-referential. What?
Okay.
Okay.
So, how would we do this? I'll give you guys.
Oh, yeah.
You guys getting pizza?
Give them 30 seconds and I'll go through it. Yeah.
Sure.
If my phone rings, it's gonna be Domino's. Just keep my phone and if it rings,
Sure.
it'll be them.
My phone is so
Rate your experience 10 out of 10. Okay. This is the second last question, right?
Yes.
Yeah, so we still have time. Yeah, so the pizza should arrive sometime at the end. No, how did the last question was that long one.
Yeah.
Oh, okay. That's the estimated delivery
What was the
time.
last one?
Last one is that long one that you're going to do, which is the... So, I was thinking about this today. This takes you back to say can I get quiet please? Settle down, settle down. Mr. Leif, settle down please. Good to see discussion, but we have to continue. I was actually thinking about this today. This took me back to like the first time in high school where you see that first time that, say, root 2 is an irrational number, and you look at that proof and you go, how the hell did someone think of that? So this is not going to be as scary as that, what we're going to do here. It's really just more following a process. But this kind of shows that once you have the infrastructure of simpler types of proofs, such as the proof that square root 2 is irrational, you can build from there these types of proofs that we're going to be doing now. So does anyone have any ideas of what we should do with this question in particular here? Yes, Mr. Justin.
Suppose it's rational.
My guy. Leif, I saw you had your hand up before. Sorry. Oh, good answer. Yes, Ver.
So, I mean, I also did that supposing. After that, I squared it,
Yeah.
and then I expanded the square, and that led me to eventually declare that p squared on q squared is divisible by
Yes.
2. And
Yep, we'll get up to that.
Squared equals to 2
Mhm.
q squared, so
Yep.
p squared is divisible by 2, then p is
Yep.
divisible by 2, and that eventually resulted in q squared being divisible by 2, which meant q was divisible by 2.
All right,
which
that's
means
that's
q
enough in my
squared
We really can't follow all that.
Yeah.
Gentleman at the back had something to say?
I know, that's kind of the same thing, like, would you set, like, P, assume P on Q is like that?
Yeah. Independent results are still good.
Answer first.
Yeah, you want to answer? What's your answer?
The combination of the 3 equals a number squared.
Uh-huh.
That's rational. It's rational, and it can't be like that.
I mean, that's where we start. That's the first step. So yes.
Correct.
What is the
What Justin said yes. Okay, yeah. So the idea here is similar to the proof that root 2 is irrational. We look at this thing and we go, what can we really do with this? We want to get rid of some of the square roots. That's what we can do. So our first step is to square it. So since I don't want to do that manually, let's suppose, as Justin elegantly said, suppose it's rational. And then we square both sides and we end up with this expression, okay? So from here you have r as a quadratic and you may not be too sure what to do with it. So what can we think about what we have to do? So let's think about which parts.
Do not solve the quadratic. If you solve the quadratic, you're going to get r is equal to root 2 plus root 3 plus root 5.
Yes, not going to help you much. So the idea here is let's look at which parts of this equation is rational and which parts of the equation are not rational. So 5 is rational. Let's keep it on the left-hand side. R squared is rational because we know that r is rational. We also know this other 5 is also rational. I guess we can eliminate these two. That doesn't really matter. But then what we can also say, what we have to say is that we kind of intuitively know that root 6 is not rational, so we kind of move it to the other side. And we're still left with the negative 2 root 5. So what we're focusing on then is this part, minus 2 root 6, okay? So if we simplify, we have r squared over 2. So this part is rational, is equal to r root 5 plus root 6, okay? Unless I've muddled something up. And what we have reduced the problem now down to, since the left-hand side is a bit annoying, but the key takeaway from it is that it's rational. So we can get a contradiction by showing that this here is not rational, which intuitively makes sense, right? Because if r is any rational number, this kind of linear combination over rationals is not going to be rational, if that makes any sense at all. Yeah. But yeah, the idea then is to do the kind of same trick again that we started off with originally. Suppose that this is rational. Say it's, what letter did I use? Yeah, like that. Suppose it is rational. We can square it again. So squaring, because we want to get rid of the square roots. And we're going to do the same thing again. So now we only have 1 square root. So we went from 3 square roots to 2 square roots to 1 square root. Can anyone guess what we're going to do next? Yes?
Get rid of the square root.
Yes, awesome. Crazy idea. Okay, so we know that this first thing, this 6 plus, yeah, very shirt-worthy, 6 plus 5 r squared plus 2 r root 30. This part is rational. Yep. So what we want to show, we also need this part to be rational. Okay, so we want to show that 2r root 30 is rational, but since we already know this part is rational, we want to show also that this part is rational. Okay, you can make the simplifying statement that it reduces down to showing the square root 30 is rational. So we have that on the next slide. We must have square root 30 is rational. And this is really just the same as the classical proof that square root 2 is, well, the contradiction. Assuming square root 2 is rational, you derive the same contradiction as we're going to do here. So let's do that. We assume it's equal to p over q, where p and q share no common factors. So again, when your high school year 12 teacher showed you this for the first time and you have never seen a real proof before for a non-trivial statement, you may think, where the heck did we get this from? But reflecting on back, the reason why we want to do this is because when you square, you can think about how kind of the factors replicate themselves. So that's what we're going to do here. We're going to make the... They call me already?
No.
Oh no, I already did that.
Oh, okay, that's fine.
Yeah, like they already paid. Yeah. We're going to assume we can simplify our rational number in such a way that it's not a real rational number. In other words, we're going to assume we dissolve all the similarities between p and q. And you've seen this before, so we're going to just go into it. We rearrange, we square both sides, we're left with p squared equals 30q squared, and we eventually, we could look at either 2, 3, or 5, but we eventually realize that there has to be a common factor on each side, because both 2, 3, and 5 are all prime numbers. Okay?
Well, if you guys have the wrong size of shirt, come to us in the end. We'll try and do a shirt swap.
Yeah. And if you have the wrong size of cards, there's more cards here.
Yes, hand in the back.
Oh,
Oh,
you
you
just-
want some cards? Too bad.
Yes, so we
Alright.
conclude that this
Root.
somewhat nice sum is irrational.
Yes. Now, some intuition onto this. Remember how we said earlier, with this lovely counterexample. Oh no, it's gone. Why'd you erase it?
Did I erase it? My bad.
Okay. Yes, the lovely counterexample, which is now living in our hearts, of 37.5 minus pi plus 37.5 plus pi. Right? Two irrational numbers adding up become rational. Okay. So the irrationals are not closed. Basically, you can have two irrationals and do operations on them, and then get a rational number. But because the rational numbers are closed, this is why we want to use contradiction whenever we have an irrational number proof. Because if we can introduce rational numbers to our proof, then we can use the fact that the rationals are closed to do all of this algebra, right? None of this would be possible, concluding that these rational parts are in fact rational, unless we assume that they were rational. Okay,
Yeah.
so you're gonna go get the pizza now?
Well, it's not there yet.
Okay. Alright, so yes. We have another food-based question. Suppose that Harry is setting up a combinatorics ball. He has a circular table with 26 seats. And essentially, every single seat has a plate on it. I'll do a small example with, I don't know, 10 plates. We have a bunch of seats. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And every single seat has a plate on it with a number on it. Now he wants the alternating sum of every group of 5 to be 29. So what that means is, let's say the first number is, I don't know, 10, 18, 15, 14. And right now I'm just going to give this one a number. I'm not going to say it's 20. This will not satisfy the condition, but the alternating sum of these 5 seats is going to be, now alternating just means every single one we change the sign. So what do we have? 10, 18, 15, 14, 20. So it's going to be 10, 15, 14, 18, 14, 20. Alternating, so we alternate the sign. Right, and if we manage to add these up, we're going to get 3, 6, 19. Okay, and this does not add up to 29. So this is an invalid seating arrangement. Okay, so we want to find all the ways that Harry can arrange these numbers to make the seating arrangement valid. So we want them to be 29, which means if we change this one to 30 and this one's now a 30, this is now 29, right? So these 5 seats would satisfy the arrangement. Come on, go away. Okay. So these 5 seats would satisfy the arrangement. But now if we look at the 6 seats, it has to satisfy that arrangement again with 18 minus 15 plus 14 minus 30 plus whatever is here, and then so on all around the table. Okay? So the question now is, if this final number is not 10, but 2026. So tech. Is it? Right. Thank you. Oh, this is so much nicer.
Yeah.
Ah.
He's in bliss.
I'm in bliss. I'm in math. No, hell no. All right, so the question is, this is the non-math question version. We call a 5-tuple of integers edible if you can label the integers a, b, c, d, e in some way, such that a minus b plus c minus d plus e is 29. So that's the alternating sum I was talking about. And we have 2026 numbers around the table, such that we want to figure out all the ways to do that, such that every 5-tuple is edible. So they satisfy this alternating sum arrangement. Okay? So for this question, I would try and find one example which works. I'll give you guys 30 seconds to try and find one way to arrange the number. Yes?
I have a question. Since it says consecutive numbers, we can assume no numbers are repeated, right?
No.
So 1, 1.
No, like when we say consecutive numbers, we mean like the first number around the table, then the second, then the third, then the fourth, then the fifth. The numbers,
No,
like the
number of bread rolls to place, like that. Can that repeat?
yes, we can have like 10 bread rolls on every single seat if we wanted. Okay.
So we can do that. Okay.
Yes, the consecutive is referring to the number's position, not the number's value. Yes.
I was just reconfirming.
Okay, no worries. So yes, guys, I would like you guys to try and find one example of A, B, C, D, E, such that you can place them, like one example of the ends, such that it allows the arrangement. Okay?
It's telescoping, so try that.
Wait, does it 26
Oh,
matter
so
anymore?
I prefer to use the, I will want to use the whiteboard.
Does the 26 matter anymore?
The 2026?
Where's 20? Oh, 2026.
No, the last part said he likes 26. That doesn't matter now, right?
That's a typo.
Oh, it should be 2026. Yeah.
Oh, okay.
Yes, also, he means this one.
Oh, yeah.
Yes, it should be 29.
29.
Sorry, guys.
How bad?
Okay, so someone said they don't understand the question. That's all right. We have numbers n1. Oh, sorry. We have numbers n1, n2, n3. So all the way around the table, n 2026. Okay, I will do the n4, n5 just for clarity. And what the question is saying is n1, n2, n3, n4, n5 is what we call a 5-tuple. That means that it's a pair of 5, well, not pair, a tuple of 5 numbers. Okay?
Ordered collection of 5 numbers.
A collection, yes. And that because they're an edible pair, right, which we've defined as saying a plus b plus a minus b plus c minus d plus e equals to 29, right? Because that's our definition, we must have n1 minus n2 plus n3 minus n4 plus n5 is equal to 29. Okay, so that's one condition. The next condition is that the next 5 have to be also edible. So if we now have n6 here, right, these numbers, n2, n3, n4, n5, n6, also have to be an edible 5 tuple. Does that make sense?
Yes.
Okay, yes?
I just have a quick question. Since the circle has no starting point, does that mean we also have to assume n2 minus n3 plus n4 minus n5 plus n6 is also
That's what I just said. I
Oh
think.
wait, that is right?
Yeah, so you will also need to have n2026, n1, n2, n3, n4 be a 5 tuple.
Oh,
If that's what, I think that's what you're trying to ask.
yes.
Yes.
Sorry, my bad.
So yeah, basically if you can, every 5 consecutive numbers have to satisfy that
Yeah,
on the
it
circle.
loops around.
Oh,
It
okay,
loops
yes,
around.
Yes, thank you.
Okay,
It's
so
like mod.
yeah.
Yeah.
Okay, so does anyone have an idea of like a way to label n1 to n2026 to make it work? Yes?
You said every n is 29.
Yeah, nice. That's really good. In fact, that's exactly the intuition you need to do the problem. So thank you for pointing that out. Oh, shut. Yeah, so one example that's pointed out is having every single number as 29. Okay? So this is touching on, right, finding an example, as we talked about earlier. If every single number is 29, right? Wait, this problem could have worked with 67. I just realized. We should, in the future. Anyways, and obviously, if we have the alternating sum of these 5 numbers, it's going to be 29, because it'll be 29 minus 29 plus 29 minus 29 plus 29. Okay, this is 29. And so this arrangement is one that works. Now, because we've already found an arrangement, right, an idea would be, let's subtract 29 from every single number and see what happens there. So let's take our original numbers, n1, n2, n3, n4, n5, all the way to n2026. And let's subtract 29 from every single one of them. So let's consider minusing 29. And the reason I'm doing this is, as pointed out, right, a circle of all 29 works. So this reduces this working arrangement to a circle of all zeros, right? And a circle of all zeros is nice because then we've had 0. 0 is a nice number, obviously, but also we can start exploiting symmetries because 29, like 30 and 28, while they are 1 away from 29, it's not really symmetric. But if we have 0, these numbers will be turned into -1 and 1, right? And that's the sort of intuition that I want to use to solve this problem. So again, minus 29. And notice, right, if our original numbers, n1, n2, n3, n4, n5, if this is an edible 5 tuple, we have n1 minus n2 plus n3 minus n4 plus n5. That's 5n. n5 is equal to 29. If we subtract 29 for each of these, we're going to have n1 minus 29 minus n2 minus 29, blah, 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 equals 29. And this will simplify down to n1 minus n2 plus n3 minus n4 plus n5 is equal to 0. So these are the numbers just subtracted, okay? So yeah, the condition becomes every single 5 tuple has to sum to 0, which is a lot nicer. And notice now that because we have this sort of thing, does anyone want to point out, right? Let's say we have 5 numbers like this, which add up to 0. We also have the next 5 numbers, n2 minus n3 plus n4 minus n5 plus n6 is equal to 0. Can anyone tell me what I can do with these 2 conditions? Yeah, add them, right? Cards. Oh, do you have a shirt? Do you want a shirt or shirt?
Sure.
I want a Jane Street shirt.
Oh, too bad. You can have cards. Justin, so generous. You can have some cards. Oh, sorry, I dropped them. You can pick them up. Yes. All right. Yes, you do want to add them. Very nice observation. Because someone else said that. Did you give them? It's fine. If you add them up, these points will all cancel out, right? So we were gonna get n1 plus n6 is equal to 0. Why is this nice? Now, the right-hand side is an even number, right? And we know that the only way to add 2 numbers to get an even number is if they are both even or if they are both odd, which means n1 and 6 have same parity. This means you guys all know what parity is, right? If you don't know, parity is essentially the evenness or oddness of the number, okay? All right, so n1 and n6 have the same parity. Because this argument doesn't actually depend on where we are in the circle, all the numbers are just labeled arbitrarily, this means that n6 and 11 have the same parity. Right, and this means n11, n7, sorry, n16, n16, n21, and so on, right, have same parity. Okay, so yes, I guess this is fine as well. This is the way. I forgot the way we did this in the thing, but you end up getting the same thing. So every number and the number 5 after it have the same parity. Okay, and so if we look at the where is the diagram? If we look at this diagram, right, n1 to n5. N1 to n6, n6 to n11, n11 to n16, so on. We can continue this chain of everything having the same parity, all the way to n2021 to n2026. Now we've reached the end of the circle over here. Right? So we've jumped from here, here, here. You can imagine the arrow continuing on all the way around the circle to n to 2021. Okay? Now when we get to n2026, we're going to jump forward by 5. Right? Nothing wrong with that. And that ends up at n5. Okay, because 2026 is not divisible by 5, every single time we do this, we're going to be offset by 1. Okay, so eventually we're going to continue around the circle 5 times, and we're going to come back to n1, which means every single number on the circle has to have the same parity. Does that make sense? Yep, all good.
When you don't ask the question as n2027?
No, it wouldn't make a difference. The only case where it wouldn't work is if this was 2025. You'd have to do some more cases. Yeah, the important thing is it's not divisible by 5, right? You know what else is not divisible by 5? Yeah. Yep. All right, back to here. So eventually you get that they are all the same parity, right? And so because the alternating sum is equal to 0, right? If they are all odd, we would have odd minus odd plus odd minus odd plus odd, which is odd. Okay, so that can't be true. So they are all even. The argument in the slides is a bit different. But in the end, you conclude that every single number is even. Okay? Cool. So now our contradiction is going to come from the fact where I guess we'll do a smaller example on the iPad. Oh, you have to unlock it. Oh, it's Touch ID. What am I looking away from? I don't know. Technical difficulties.
Just 1 second. We'll
One.
be right back after this advertisement.
All right. So yes, our idea here is now, because everything is even, right? Everything has a factor of 2. What can we do about that? One thing we will notice about our condition about our conditional numbers, which was a minus b plus c minus d plus e is equal to 0. We've shown that these numbers have to all be even. So let's let them be 2a, 2b, 2c, 2d, 2e. Okay, now this is this is kind of reminiscent to our proof that root 2 is irrational, where because we assume we've proven that something is divisible by 2, so we want it to be 2 times some integer. Let's replace them. We get 2a minus 2b plus 2c minus 2d plus 2e is equal to 0. Why is this good? Because we can divide the 2 out, right? So we get a minus b plus c minus d plus e is equal to 0. And notice that a, b, c, d, e, capital, are now also an edible 5-tuple. Okay? So if our numbers are all even, we can construct another example from them. Does that make sense? All right, so our contradiction is going to be, well, the idea is, right, if you have some all even case, you can reduce it down to a smaller case, right? And eventually, we should be able to keep doing this because we've concluded that whenever we have a circle like this, they have to all be even. So A, B, C, D here have to all be even as well, right? Otherwise, they wouldn't satisfy the condition around the circle. So we're going to assume that we have some solution where the sum is minimal, okay? Now, as we've shown, we can divide every single number by 2 and still get a solution set, okay? So if we divide it by 2, the new solution has a sum of s on 2 smaller than s, which means that it's not a minimal solution. And essentially, we can keep doing this onwards and onwards. Well, we've already got a contradiction, but this is what we call proof by infinite descent. Right. We assume there's a smaller solution, and then we show that there's a smaller solution than that still. Okay, so the only solution is when s is equal to 0. And that is exactly the example where you came up with, so good job. So the solution where everything is 29 around the circle is the only solution, as you can see. All right, yes?
If you go back up to, like, you get n1 plus n6 is 0. There's like like when you're working on the left.
Where? Oh, like here. Yeah, sorry. All the way up here, you get, nope, it's down. It was down, in fact. You get,
But if n1 plus n6 is 0, surely n1 is equal to negative n6.
yes.
And then you can kind of apply that same thing,
Mhm.
showing that they actually just all have to be equal to each other.
Well, they'll be negative to each other, like negative equal to each other.
But eventually you'll get back
Mm-hmm.
to, like, you'll loop all the way around
Mm-hmm.
such that.
You get back to 20. Are you saying, well, yeah, I see what you're saying. We start here, right? We've proven that n6 is negative n1.
Yeah.
So n11 is n1.
Yeah.
And n16 is
Yeah,
negative
that's
n1.
showing-
And you keep doing this to get to 2026, right?
Does it keep? Can you keep looping?
Yeah, you can
around
keep
such that
going.
n1 is equal to negative n1.
That depends. I don't know in this case if it's like the parity works out properly. Is it you will loop around 5 times. There's 2026 numbers, so I think yes, that will be the case.
In which case,
Yeah, it will have to be equal. They will have to all be 0.
I have to always.
Yeah, that's another way to do it. But we wanted to showcase the proof by infinite descent on this one.
Okay.
Yeah.
There you go.
But yeah, good observation. Any questions from anyone else? Okay, so that's all the problems we had prepared for today. Thank you all for coming. Oh, wait, right. We should go over what we're going to be doing now. Why is it cropped? Okay, I don't know. Wait, why? What the hell?
We still have 15 minutes. though.
Hold on, gang, why? What is happening here?
Just keep it up. So if you haven't seen the attendance form, yeah, we have pizza coming. That should be here in around the last 5 to 10 minutes. But of course, like I don't think anyone's in this room afterwards, so we can just stay here and have the pizza. You have the worksheets. Try the worksheets. If you
We'll be coming
wanna-
around.
If you want to annoy us about the worksheets, annoy us about the worksheets.
We're not being.
Before that, let's
Why are you
take-
saying annoying? That's negative. No negative connotations here.
Positive.
Ask us about the worksheets.
Yeah.
Before that, we want to take a group photo, so we need to get a photo with the outline. So can we please do that now? So we need everyone at the front, please, to take a photo with the banner. Nice little group photo doing math.
Justin. Sure.
If you can take the photo, sure.
I can help you take
You gonna hold it?
We're holding it. Do you want to hold it?
You said Justin, so that's what I think.
Oh no, we just want you to be here.
Okay, well, I'm gonna
Come on,
Everyone,
come on.
Yeah, be behind. Let's maybe put like the little funny
Make sure Justin's hair is in frame.
It'll be in the frame anyways.
Whoa, it's flickering
Oh,
now.
that's crazy.
Okay. I think the projector just hates us.
So
Lovely
that
slides.
was us before. It's gonna be us in a second.
Yes.
Yeah.
No, I think
Oh.
this is us already.
Yeah, tasty and thinky. Yeah. All right.
That was a good one.
Jeff's gonna take
Thank
the
you.
photo. Can you take it on my phone?
Why is
I'm not gonna put it on my phone.
Did you consult with Alan today?
No.
Everyone
Oh.
huddle in, please,
You
huddle
didn't
in.
tell me. This is your fault.
My bad.
Bring the banner to the front a little bit. All right.
Come in. Come. You guys can come behind us. You guys come behind us. Justin, in the middle,
Get everyone
please.
in, Jeff?
Okay.
Yes.
Fine.
Yep.
Alrighty.
Wait, hold on. Is this centered? Is this centered? Pull a bit more to that side. Okay. Look good?
All right, take a few.
All right, thank you.
Wonderful. Awesome.
All right. Cheers, everyone.
Stay for the pizza. Please try the worksheets.
I really strongly recommend next one pizza first because we are hungry and right now.
If we gave you the pizza first, you wouldn't stay.
Oh, sure.
Yeah, in the middle,
Oh, you
at
leave.
least.
See you, boss. Yes, we do have pizza coming. It'll be kind of weird.
Hello.
What's the ETA?
How are you? I like the question you did. You know the interval one?
Yes.
I remember that from somewhere.
I don't think I explained that one very well, but it's fine.
Oh no,
Hello?
I'm saying I liked it.
Oh, hi.
You have a question?
Something like this one, are you setting like ABC to like some like 2K plus one?
Does everyone have a worksheet?
Well, you can do that, yes. I think usually remember how in the question where we had root 3 plus root 3 plus root 5 is irrational, right? We didn't substitute that to be P on Q until the very end.
Oh, okay.
You want to try work with unsimplified as long as unsubstituted as long as you can.
Genuinely.
Because you get less algebra, right?
Okay, yeah, that is true.
Otherwise
so-
it's too long, I guess.
Yeah, I suppose.
So instead of saying A, B, and C are odd, why don't you the contradiction is we want this to have a
Assume
rational
there is
root.
rational root.
Yeah, so let X be P on Q, right? And see what you get from that.
Ooh, okay.
Did I ask you a question, Kevin?
Sure.
This is a different question. I'd asked this on the Discord as well.
Mm-hmm.
I'm still confused about one part. This is a round robin question. Erdos made a theorem about it in the paper.
Yeah, were you the person who wrote that?
Not me. I mean, I wrote this.
No one wanted no, say
Oh, yeah. That was me. I thought you meant the paper, obviously not.
Anyone want more cards?
So I guess the whole point of the question was to...
We try not to give all of them out. Okay, limit to 2 packs per person, please. No, we're gonna keep them for future reference.
You're gonna keep them.
Oh, I mean, I can bring them to future reference.
Or you could keep them for the next competition.
So much better than two of
Math question.
I do want to keep them. They're very nice.
I'm not seeing enough work in these worksheets.
I know the whole question is basically constructing Erdős' proof. So I had basically thought about calculating the probability of essentially everyone being beaten in 1,000 and then doing the selection of the sets and then basically showing that that thingy is less than 1, which means one person. I'm gonna have to recall.
No, you're gonna the proof Erdos had is in 1,000, right?
Yeah.
Finding the probability where there is no person who beats everyone.
Yeah, in that 1,000. Yeah.
So and you show it's less than 1.
Yeah, I showed that that's less than 1, which means one person can beat 1,000. My only issue is there were 2 people on Discord saying this ends up going into linear expectation. So I was a little confused. But I looked at Erdős' proof.
I don't think Erdos was check had that.
Yeah, it didn't. That's why I got confused.
I don't know what. Okay, if you can do correct.
I mean, I double checked.
If you want to send this to
I already did post it.
like this PDF.
Oh, no, just oh my god, screenshot of the question.
Is this just study fast?
We
If
may.
you want to send this, if you want to send your proof, to us on Discord,
Yeah, let's put on the map channel.
Oh, okay, thanks. I mean, that's what I did in the past, which is when they...
we saw your stuff very nice.
Oh, okay. But I really like this workshop. I'm actually kind of bad at the non-probability sides of things, so I found it pretty helpful.
Good that you enjoyed. I think we might have to leave the room. I'm not sure if other people can. There's your charger, by the way. Yeah. Oh, thanks.
Did you find the USB-C attachment?